from City University of Hong Kong. It's my great pleasure to chair the second session of AG webinar. So today we have two great speakers, Professor Daniel Cohen-Or and Professor Lin Gao. And they are going to talk about how to use deep learning to generate photorealistic images and possibly with some intuitive editing. So this topic is very important in both the communities of graphics and computer vision. Yeah, I'm particularly happy here because both Danny and Lin, they are my good friends and also collaborators. And we are also working in similar fields. So let's start the first one. So the first talk will be given by Professor Daniel Cohen-Or. I call him Danny, maybe for short. Okay. So Danny is a professor in the School of Computer Science at Tel Aviv University, Israel. And he got his PhD degree from Stony Brook. Personally, I owe to Danny a lot because I think he somehow helped me to start my career, and he helped me to publish my first SIGGRAPH and also second. Danny is a very important figure in the field of computer graphics, and not only in terms of the quantity of the publications and also as well as the quality of his research. And so far, I think the past 20 years, he published over like 100 or even 120 SIGGRAPH papers. And this is really amazing. And so his research has been recognized by various awards, including SIGGRAPH Computer Graphics Achievement Award in 2018. And recently, a Eurographics Distinguished Career Award. Yeah, so let's welcome Danny and to give his talk, Generating and Editing Ultra-Realistic Faces. Okay, so the stage is yours, Danny. So I will stop sharing.
Yeah, okay. Second, screen two. I think I need to share this one. It's the wrong one. Oh no, wait a second. Okay, is it right? Do you see the right screen? The right thing?
Yeah.
Okay, cool. I just want to make one comment. You know, you mentioned that paper that we had in 2007, and I think this is was one of the first papers that uses machine learning at that time in graphics. And it's amazing to see now, 14 years later, that at least all my papers are on machine learning, and I think also yours. So we reached to that point, yeah. And so today I will talk about generating and editing ultra-realistic faces, yeah. So I'll talk about generative models, and I assume that all of you know that this generative model made a huge progress during the last few years. As we can see here, since this the paper of Goodfellow from 2014, we can see a huge improvement of the quality of the images, especially for faces, as you can see here. And I would say that today, StyleGAN is the state of the art for faces. As you can see here, the quality is really high, and in most cases, I mean, it's almost indistinguishable from real images. And I think we all saw that, but you know, I put these images here. This is a random sample of a normal distribution, and I think it's amazing to think that this is simply a peak of a random noise feed forward through a network, and just a series of convolution generates such realistic faces. And I'm saying this is not cherry pick these images, and I believe you all saw this site called "This Person Does Not Exist," when you can generate endless synthetic images of this, what I call ultra-realistic realism. And I would maybe leave this this image here for maybe for 3 minutes, just that we digest that this is a synthetic image. It was generated by a network. And okay, for this case, I must admit that this is a cherry-picked image, but of a random set. And I must say that in the last year, it's exactly a year, I think, I've been working a lot with StyleGAN and published maybe 8 papers on that topic. And yet I'm still amazed by its performance. And, but you know, StyleGAN is more than just a great generator. It also has interesting properties, as we're gonna see now in my talk. And for example, here we see how StyleGAN was leveraged to manipulate the Stephen Curry pose. I mean, and I know that we got used to see these kind of images, but I want us to remember that Stephen Curry here was not part of the training data. And here we have an example of Taylor Swift. We changed her hairstyle. Yeah, and we're gonna see all of these. And here we changed the age of some person. And note how all the stages are quite realistic, and we can change it forward and backward and keep the realism. And we also can obtain a tonification version of human faces. So I kind of think that we all kind of saw it, but now let's see, as I said, let's see that StyleGAN is more than just a good generator that generating ultra-realistic faces. But let's dive a bit into the architecture, because I think it's important for the rest of the talk. So StyleGAN is just like any GAN. It receives an input, a Latent code. Let me use the pointer. A Latent code from a normal distribution and generate an image, yeah? But there are 2 key differences between the architecture of StyleGAN and previous generator. First, in StyleGAN, it has a special Latent code that is called W, in addition to the standard one. And it has a mapping that maps this normal distribution to that learned Latent code. So it's learned, and the mapping function is learned during training. So this Latent space has a normal, doesn't have a normal distribution, but it has, since it learned, it has a distribution which normally fits to the training data. And that's what will make it what we call disentanglement. We have this disentanglement property. The second difference is that this Latent code is injected to all the layers of the network. So it gains some control of different level of details of the image. We're gonna see that soon. And there are 18 maybe layers, but we can see them and regard them as if we have 3: coarse, medium, and fine. And the cool thing is that with disentanglement, we can do some mixing. I mean, let me explain that. Each layer control, as I say, different level of details. So what do we see here in this image? The first row and the first column are just images sampled from StyleGAN. And each entry is a mix between the 2. For example, this boy here, it's a mix of this boy over here and that woman over here. And let me explain that a bit more into details. So this boy was generated with W1. This is its Latent code to generate that. And for her, we have W2. Now, in order to do the mixing, we generate this boy by taking W1 into the coarse level of the generator, and the rest of the levels are taken with W2. So we get this mix where as you can see here, it has the coarse properties of the boy, the face size and his age, and you get all the rest from that woman. Or we can see another mix. You can see here the fine details. You can see that woman here is her fine details, or let's say the color to be more clear, are taken from the image above. So we can do this type of mixing, and they are disentangled. And now, also another amazing property of StyleGAN Latent space is that this Latent space W we can traverse it and control all kinds of semantic attributes. For example, if we start from an image here and we have W, we can traverse along a path in the latent space, for example, and add eyeglasses to her face. Or if we do go to another direction, this kind is linear, we change the pose. And all that is performed on a pre-trained StyleGAN, where the manipulation is just manipulating the input latent code only. We don't need to train anything. And these are two examples, but we can do other kind of editing just by traversal the latent space. We can change the age, the eyeglasses, as a generator, we can change the pose, the expression, we can add wrinkles, all kind of semantic editings, all applied in the latent space. And what I like, this is a very simple example where this is a traversal along a linear path, and we can see how we change the pose of that boy. And you take a look and you can see that the ID remain the same along the path. And I think it's quite amazing. Okay, so we see all these nice edits, and a natural question is how we can use these amazing editing capabilities on real images, like on these celebs here. So what we can do, we would like to do editing in latent space. We need to take the input image of the target image and invert it into the latent space. So we need to find the corresponding W that if we insert that W into the StyleGAN, it would reconstruct the original image. So the process with which we find the latent code to correspond to that image is called inversion. So how do we do that? That was presented in that paper, StyleGAN, image to StyleGAN. It's more than a year ago. We start with a guess of a W, could be the average. We insert it into our pre-trained StyleGAN, get, in this case, the average image. We compare it to the target image, and we update W through a gradient descent, for example, here. Okay, we applied it several times. This is an optimization process, and it slowly converges into that image, which is good approximation of Obama. Yeah, it's not bad, but not good enough. Yeah, and what the authors concluded, that W is not expressive enough. I mean, okay, W is quite huge, but you cannot generate all real images or express them with a W. So now things become interesting. So what is suggested is to extend the latent space. So instead of W, in W, the latent code is injected to all the layers of StyleGAN. Instead, in W+, each one of the style code can be a different code for each of the layers. So the extended latent space W+, now it's called, it's much larger than W. Actually, it's 18 times larger in the size, yeah, of the codes. And with this rich latent space, we can actually reconstruct or generate any image, actually. I mean, but for faces, we can get really close. So if we do the optimization, and now we do it with W+, we can get that close to Obama, much closer than before. And to emphasize that, I put them here, so we can see that in W, we get kind of a much younger Obama. And here, the reconstruction is much better, or almost perfect, yeah? The thing is that it's quite slow. It's much better, but it's quite slow. It can take a few minutes even. And then we cannot use it for real-time application, for example, or as part of image-image translation. Okay, so another approach is not to optimize, but to train an encoder. We can train an encoder text and image as input and predict its corresponding W in W+, yeah, that reconstruct the image. We can do that. I emphasize that this is a frozen, yeah, StyleGAN. So we have an autoencoder. We train it and train the encoder, and we get reasonable result. That's what they did in that paper. ID invert also. I feel all the papers nowadays are a year ago, but it's not that simple as it looks like. I mean, you can see here that the result is still not good enough. It resembles more. I mean, it resembles Obama, but it's not good enough. And that's what brings me to our paper that we worked on it exactly a year ago, or yeah, worked on it a year ago. It's called Encoding in Style, where we developed an encoder for StyleGAN. And part of this, I won't go into all the details of the architecture, but I will just say that that part of the success of this encoder is because it uses features which are designed to have features of 3 levels which correspond to the 3 levels of StyleGAN. So we call this architecture pixel to style to pixel, because we start with pixel, convert it to style, and then back into pixel. So pixel to style to pixel, we call it PSP. This is the PSP encoder, which perform quite well, and we train it with 4 losses. Okay, we need the 2D loss so that 2 images looks alike. We use a perceptual loss, a localization loss, so that the search will be around the average W. And the important one is the addition of this identity loss, which is based on a pre-trained face recognition network. And this ID loss helps a lot. And you can see that it gets really close to the original ID. So this is only one example, but I can show you these examples. You can see that the inversion, or if you like, the reconstruction is quite good. It's not perfect, but it's very close to the original one. And if you may think whether this is a cherry pick, probably these examples are cherry picked. But if we compare it to the previous technique, it's much better. Okay, cool. So this looks great. I mean, we have an inverter that do a reasonable inversion, but then once we have the inversion, we can apply it to do some editings. We can change the pose, the gender, the age. But if you look more carefully, it's not the type of editing, the quality of the editing is not what we would expect. I mean, look here in the pose, we have some artifacts here. Here, we change the gender, the hair is incorrect. We have some, again, more artifact. Here, the face is also a bit squeezed. We have all kinds of artifacts which are not good enough. And why is that? There's still, I mean, there's a big gap between a good reconstruction and a good quality of editing. So here we made, with the PSP, we made an effort to go to somewhere, to some W in W+, so that it can reconstruct the image good enough. But as you can see, it's not located in W. And W+, as I said, is much bigger than what is illustrated in that image. So it's away from W. W is where the generator was trained on, and it's a bit away from it. So in W+, not all the region have good editing properties. So that's exactly, so analyzing and understanding the difference between W and W+, it's quite interesting. Not to say complicated. Things become complicated and more interesting for us as researchers. Okay, so this brings us to the next paper where we analyze the trade-off between W and W+, and actually design an encoder which has a good balance between the reconstruction and editability. So let me show that to you. So first, let's see again some examples here. We clearly see that we have a good reconstruction quality, both of PSP and the optimization. Maybe the optimization is a bit better, but we have good quality or the quality of reconstruction is similar, but the editing is not. I mean, this is completely wrong, yeah? And we can see similar example here also on cars. We can see that the editings here in W are much better than the editings in W+, you can see that as you see here, you can see here that there are some distortion on the front of the car, or maybe here the grass is not green as it should be. The quality in W, it's not surprising. Actually, we observed that, but it's not surprising in retrospect and looking back that the quality of editing in W is much better than in W+. Maybe not in all places in W+, but on average. So what we can do? So how can we design an encoder that has a good trade-off between reconstruction and editing? So I'll try to explain it with this briefly, yeah? So we have to remember that W+, here it's written W, it's wrong, but it should be in W+. It allows all the style code to be different, right? That's that W+. But the inversion itself does not constrain the style code to be in the distribution of W. Yeah, W, it's a distribution which is learned, so it's not easy to be modeled. It's not modeled explicitly. So therefore it's hard to make sure that the inverted code reside inside the distribution of W. So what do? We need to understand a bit this figure because I like it, and I think if we get deep into it, it helps to understand the relation between these two spaces, W and W+. So let's assume the W is one dimension. So we have, in here we have two style vectors, style 1 and style 2. Actually, we have 18 such styles, yeah. But we have, for the illustration, we have only 2, 1 and 2, and each one of them is one dimension. So along the diagonal, all the styles are equal, yeah, from style 2 and style 1. This is the diagonal, and the red points represent the distribution of W. These are the red points. This is the distribution of W, and W+ is the entire space. It's away from the red ones. So now we take a look at these blue points here. These blue points are highlighted in W+ because they have, like the one illustrated here, it has the two coordinates which are in the distribution of W. So this is a good point. Each one of these coordinates is inside the distribution of W. It corresponds to a red point on the diagonal, yeah? So this point is a relatively good one, or all these blue points here. But we noted that as we get closer to the diagonal, we get better editing. We explore that through a lot of experiments. And then what we do, so we design an encoder that predicts the latent code in W+, but as close as possible, we push it towards the diagonal. This is the red arrow here. And also, each style vector get closer to the distribution, like here or here, the distribution of W. So it has two losses that pushes it close to the diagonal and close to the distribution of W, and we get a good balance. I mean, it gets close to W, there is enough space there, so it gets a good reconstruction, relatively good reconstruction, but especially the quality of the editing remains high. And I like this example here a lot. See the difference between E4E and PSP. The PSP is the previous encoder. The E4E is that new encoder. We call it E4E because it's encoding for editing. We do an encoder especially for editing. And if you look carefully, you can see that the editings here, the quality of the images are much higher. I mean, it's more alive and more crispy. Many of the details are much better. I can run it maybe again. Never mind. And and I must say that emphasize that the reconstruction quality is not perfect, but we compromise the reconstruction for the sake of editing. So the editing is good. And we need to remember that doing an inversion just for the sake of reconstruction is meaningless. I mean, we have the original image in hand. The whole point of inversion is to perform an editing, and that's what we do. So this is an encoder for editing. And it's not only for images, also on cars, we can compare the quality of the edits, and you can also measure them. compared to previous encoders. And the reconstruction, and the reconstruction, as I say, we gave up a bit on the reconstruction quality for the sake of the editing. So in the optimization, for example, which takes a long time, we can get a good reconstruction, but not good editing. While in E4E, we get close to that, but with the editing are good. So it's still not, there's still a gap between E4E and the quality of reconstruction, the optimal one. So the question is whether we can do better. And I would not have asked it if the answer would not have been yes. So in our follow-up work, we proposed a general framework that further improved the reconstruction of the encoder. We call this encoder Restyle. And the idea is quite intuitive, and I'll try to explain it. So instead of the encoder, instead of directly predicting the W of the reconstructed image, we predict a residual. So we take two images. One is a guess. We start with the average image. That's the average image. And the encoder sees both of them and encode a residual that we add to the latent code of that image here. So we add it here and reconstruct the image. It's not, doesn't get exactly the same thing, but now we can reiterate. We can take this image and put it now as the guess. Do the same thing. We compute the residual, update the code, and reconstruct the image with the StyleGAN. Much better. And we can do that, you know, we do that for 3-4 iterations, and it converges to much closer to the original image. So it's an iterative, that's why we call it Restyle. It regenerates styles. And so I would say that this encoder learns to optimize. In the optimization, we do many steps. We do thousands of steps until it converges to the right location. But now with this iterative encoder, we learn how to optimize, and we do that with 3-4 steps, and we get quite close to the best reconstruction. For example, you can see here, the reconstruction is much better, and it takes less than a second. Yeah, the inversion. I mean, a few iterations of feed forward. And here I show some examples. I mean, how it improves. I mean, this is the first guess, the prediction, and slowly, maybe not slowly, quite fast, it reconstructs well the original image. Okay, so where the time? Okay. So in a recent work, we did, that's also from our lab, we take a new approach for inversion. And the idea is to allow a gentle modification of the generator weights. So here we do change the generator. It's not frozen like we did before. And so we do so only after having an inversion. So we first do an inversion and then optimize the generator around that inverted code so that the encoder can generate well the input image. So we can get images like this. I mean, it yields a very accurate reconstruction of the original image. And not only that, now we can also go outside the domain. This image is outside the domain. In a sense, it's not a normal image. It actually has a makeup or some makeup on her face. And still, if we just apply optimization, it cannot recover these out-of-domain marks on her face, or of course also the E4E cannot. But now with this fine-tuning of the generator, which doesn't take a long time, it's only a few iterations, we can get a good reconstruction of the original image. And also for celebs, I mean, the quality gets really, really close. So we do some fine-tuning on the generator to get a perfect reconstruction. Okay, one thing I didn't say, I mean, once we have an encoder, we can use this inversion to do some image manipulation. And I'll show you some of the examples. In one of the papers in last year's SIGGRAPH, we published a paper that only focused on age transformation using this StyleGAN techniques. And I showed that before, but I think it's worth to show you more example. Okay, as you can see, it's one. You can see how the age changed, and again, I encourage you to look carefully how each of the frames look realistic, and it goes forward and backward. I mean, in time, in the aging. And this what we show in the paper, it's not a linear. It's a non-linear traversal in the latent space. And we could do also other kinds of things. For example, here we have we can do image-to-image translation. We can train the encoder to take a segmentation image and predict a real image. And we can get different kind of result just by mixing. I mean, with this technique of mixing, we can change the fine details of the image with some examples, and we can get different realistic images that all agree with the segmentation. And we can do that also with sketches. We can train an encoder to take sketches and convert them into these images. So it's not only faces of humans. Can take any. Actually, we can work with any pre-trained generator. I don't get any feedback from you, so I don't know if I'm speaking to someone. Hears me? Oh my God. Hongbo, do you hear me? Let me stop.
Yeah, I can hear you.
Ah, you hear me? Okay.
Yeah, I was
I
muted.
have the feeling that I was speaking to
Yeah.
Okay, cool. Okay. So where I was. Okay, so I showed that we can train the encoder as part of an autoencoder to do all these kind of paired image to translation. And another example of type of editing that we can do is something that I really like. It's called patch editing. I mean, what we did here, we take the image of Ubana and do a patchwork, put some eyes of someone else on his face. And now when we take that image and we do the inversion, it inverted into the latent space of W, which doesn't recognize this kind of patches. So it reconstructs a real image, and you can see how well it blends into his eyes in a very convincing way. So we call it patch editing. And there's much more thing that we can do once we have a good encoder, of course, a good generator, the StyleGAN, and a good encoder, like an encoder that they can take an image and gets a reasonable or a good inversion. Okay. Yeah, fine. So I see that I'm talking half an hour, right? So we have time. So I'll show you more things. I mean, I hope that many of you, let's say, saw this style clip. And yeah, we're approaching the end, so I have a bit of time to show you that. I thought that maybe I wouldn't have, but I want to show you the style clip for those of you who didn't see it. It's okay. So here, we try to answer the question, can an image be manipulated with just the guidance of a text only? I mean, a text prompt. And I mean manipulated, and I mean also a photorealistic image, like we see here, and a realistic editing, and all this only with text. So let me demonstrate a bit some example. For example, here we take the image of Leonardo DiCaprio, and we type a prompt, blonde hair, and the hair is turning into blonde. Yeah. Or if we type angry, it gets angry. Or if we change, we use a bobcat hairstyle, you can see that how his hairstyle is changing. And you have to remember that these edits are disentangled in the sense that only the relevant attributes are changed. Yeah. So we change only the hair as expected, and the face remains intact. Yeah. I show that again. So again, I won't get into the details, but generally speaking, the idea is that we merge or we leverage the power of two strong networks. We take StyleGAN, that's what we did, and we take Clip, and we bring them together to create StyleClip. So only the feedback that or the losses that we apply are based on Clip, which Clip is a network that compares text and images and give the feedback on the dissimilarity between the two. So conceptually, it's very simple. Just take these two networks and put them together. But in order to do it right, we need to take care of the speed, to do it properly. So we have a disentanglement, as I showed, and we want to apply it on real images. And now, of course, with this encoder that we developed, we can do all these games. And this is the first author, Or Patashnik, of StyleGAN, StyleClip. And here she played a lot with her face and used different celebs and changed her, modified in a very convincing way her face to all these singers. I don't know, Beyonce, I don't know who knows them, but Hillary Clinton. I think it's quite fun. And many people around the world already play with it. There's an open application that anyone can play with it. And I like a lot this example here. When we use the image of Ariana Grande, I didn't know her before this project, but here we do an inversion. And then we write a tanned woman, she became tanned. We write a woman without makeup, and her makeup is removed. I mean, I think this is an amazing example, because otherwise, how to remove the makeup of someone? I mean, and this is not that we tailored an application especially for that. We just wrote the text, and it removed the makeup in a convincing way. And there are different things we can play with. For example, the most fun is to play with the hairstyle. For example, here we take this image, do an inversion, and we can change with this text only. We can change the hairstyle. And through this project, I learned a lot about hairstyles. I never knew what is bobcat hairstyle or mohawk hairstyle. Curly hair I knew, and this is bowl cut, and it's very easy to play with. And as you can see, it changed only the relevant part, and in a convincing way. So that was StyleClip, and I assume that you all saw it. But there's a new work that I think probably it's quite new. It's from August, when we didn't publish it yet. It's on archive, and we call it StyleGAN-NADA. And here it's also a machinery which is clip guided, but here we train a generator. I mean, it's not that we apply it on an image. We use it to train an encoder. Sorry, I'm confused. To train a generator, and we change the domain of generator only with text only. So we train, if you like, we can say it's a blind generator, or we train a generator without any image, just with clip. So here are some two examples. I hope that we show a number of results, because this is generator. We can generate many samples of that style. Or I hope you know who Nicolas Cage is, because this is really a fun example. This dog really looks like Nicolas Cage. And we can generate as many results as we like. And here we do, again, we do an inversion. The nice thing that we use a basic encoder as generator. I keep confusing, and generator. And then we train a generator for Cubism or for Modigliani, we can use the same W for that generator. And as you can see here, we can easily, once we train that, it doesn't take a long time to generate. We generate a generator, and then we can do all these kind of inversion, of conversions and display them in all these kind of styles. And to convince you that this is really a generator, I'll show you that video where we trained and developed how many? 8 generator here, and we take that image in the center, and we not only that we generate these images, but these images are for generators, so we can apply all this editing that I showed you before with that generator. So we train here 8 generators, and we can do all this kind of manipulation on that on this generator. And I think it's quite cool. And I also played to have some fun. I mean, of course, you know, the next Sigurd chair, Niloy Mitra, we played with his face. Olga, you all know Olga, I hope, and Kavita Bala, and myself. And my student also, they keep playing with it all the time, so they make fun of me and try all kind of version of myself. Each one of them is a generator, but it's very easy to train it. I mean, you just type a text of some figures or some text, or for example, here Botero, which all the faces are fat, and they generated these images. And these ones, I don't know if you're familiar, but this is Modigliani, and this is the Mona Lisa. I also have a version of Mark Zuckerberg as a princess, and it's quite fun. Okay, and this is Cubism here. Cool. So all these papers are listed here, and thank you very much. If you have questions, you know, I don't see any face in front of me, but I can take questions. Hongbo, maybe there are more in the on the chat. I don't know.
Yeah, yeah. Thanks, Danny, for the wonderful talk. Yeah, so far I haven't received any question yet. Maybe I'll start. Oh, okay. There's somebody. Well. So maybe I'll start with a general question first. And yeah, I'm impressed by the quality of the generated images. And yeah, as you know, I'm also I've been working on similar projects. And from time to time, I think we were questioned about the ethic issues, right?
Oh, don't ask me that. Don't ask me that. It's not a good question for Israelis.
Okay.
No. I don't know.
Yeah,
you know,
I don't personally. I don't care about that. I think it's just like when you make something good, it always has 2 sides. And
yeah, right. Yeah.
Yeah. Okay. And then okay.
Many technology you can use wrongly. It's not. I don't think it's our.
Yeah, but we will always question. You know.
We can do such beautiful thing with that, and for the movie industry, for fun, for entertainment, there are many interesting things to do with it. I mean,
right.
To do malicious things anyone can do with many other things.
For sure.
But it's not.
Right.
As I say, it's not a good question for you.
Okay, and let's see if I receive any other questions. Okay, I think maybe I can ask one more question, and then I think, yeah, we are about. I can maybe okay. So at a certain point, I think you maybe there's one question. Let's see. Okay. I got one question. So in Chinese, I try to translate. So for the editing or the style transfer results you demonstrated, can they be applied to like glasses or hats, like accessories in different photos?
They ask if it's possible. What's the question?
Yeah, whether like this can be applied to like accessories like glasses and hats, and then this kind of style can be transferred to.
I mean, that's one of the challenges now. I mean, hats, if they appear enough in the training data, I think hats, glasses, and things which are quite common, I think the generator can handle them, but not very well. It's not. But basically, I would say that it can manipulate well within the domain of the training data. But I mean, I think I showed, it's not only me, but we show amazing results. But it's only the start. I mean, there's a lot of limitation. I mean, all this works really well for faces where the faces are structured, you know, the eyes are more or less the same position and so on. And it can really handle well structured images and with not a very rich variety in terms of the structure of the image. I mean, and it especially works really well for faces once you go to half body or full body or, you know, outdoor scene. There's a lot to be done and developed. It's only the start. I mean, we are lucky. I think it's in the years to come, we need to extend and improve all these capabilities to general images. There's a long way to go. But specifically for his question, I would say that hats and glasses, which are common on in these images, you can handle it.
Right. Maybe there's one, probably the last question from Ha-Wan Song from YouTube. So how do you handle the light contributing to the image data? I'm not sure about the light. Is lighting?
You can change. There's some control on the light. Yeah, it works. I mean, but you know, you have to remember that all this control, we gain them without supervision. I mean, the training data doesn't have any tags, any information, and it's so everything is unsupervised. So if we want to handle light and to do it with a bit of supervision, I think it's possible. I mean, I think that there are some works on that, not in the context exactly of StyleGAN as much as I know, but it's again, it's a good direction to research. There is some control on the light direction, a natural one, but it won't be an elaborate kind of lighting.
Okay, so I think we are running out of time, right? So let's thank Danny again for the very interesting, inspiring talk. I think maybe just receive my okay, yeah. So thanks.
Okay, so I released my. Thank you very much, and I stop sharing.
Okay, thank you.
Bye.
Bye. So I will share my screen. So let's move to the next talk. So the next talk will be entitled "The Deep Face Generation and Editing with Sketches." So the talk will be given by Dr. Ling Gao. Dr. Gao got his PhD degree from Tsinghua University under the supervision of Professor Siming Hu. And Currently, he is associate professor at the Institute of Computing Technology, Chinese Academy of Sciences. His research interests are mainly in computer graphics, geometry, processing, and visual media computing. I think he is kind of like a rising star in our field, and his research contributions have been recognized by multiple awards, particularly recently by AsiaGraphics. He received the AsiaGraphics Association Young Researcher Award. And let's welcome Dr. Lin Gao. So it's your stage.
Yes. Thanks a lot for that. Thanks a lot for the invitation, and thanks a lot for Hongbo's introduction. Now I will share my screen. Yeah. Now let's begin my talk. And today the talk is about the DeepFaceDrawing and editing using the sketches to generate the face and to edit the face. Creating realistic human face images from sketch benefits various applications, including criminal investigation, character design, educational training. Facial editing also has a great positive influence on the progress of social media and the movie industry. However, it is not easy to achieve excellent face drawing and face editing results. Face image generation is time-consuming. Even for professional painters, it requires more than 2 hours to draw the realistic face images. Besides, face image editing has also high cost. It requires professional software and complicated operations. Existing methods have tried to solve the above problem, such as Pix2Pix could synthesize realistic images from sketches or thematic masks, but it is difficult to generate high-quality results. FaceShop could also edit face image with masks, simple sketches, and colored strokes, but it could not edit facial details like wrinkles. For our approach, we aim to generate high-quality facial images from raw or even incomplete sketches. And given realistic facial images, we could edit the appearance like hair color, skin color, and lighting. Besides, we could also the geometry like facial component and hair structure. First, I will talk about the DeepFaceDrawing. This is the joint work with Professor Hongbo, Shi Hong, and Shu Yu and Wan Chao. This work is to translate from the sketches to the realistic images, from the freehand sketches to the photorealistic face images. Creating realistic human face images from sketches benefit various applications like the criminal investigation, character design, educational training. Due to their simplicity, conciseness, and ease of use, sketches are often used to depict the desired faces. Drawing face sketch needs professional training. We need first to determine the facial structure and then depict the facial details. When drawing a realistic face image, it is also necessary to considering tone correctly. For novice user with little drawing skills, it is hard to achieve such tasks. Could we translate freehand sketches to face image? The recently proposed deep learning-based methods, such as image-to-image translation techniques, allow automatic generation of photo images from sketches for various object categories, including human faces, and this method leads to impressive results When these methods are applied to the sketch-to-face task, we would get a result like this. This is not good because this synthesized face image exhibits a lot of artifacts. Most of such deep learning-based solutions for sketch-to-image translation often take input sketches almost fixed and attempt to infer their missing texture or shading information between strokes. Since they often train their networks from pairs of real images and their corresponding edge maps, due to the data-driven nature, they thus require test sketches with quality similar to their edge maps of real images to synthesize the realistic face images. However, edge maps are difficult to make, especially for the users with little training in drawing. Users will draw the freehand sketches like this. In our work, we aim to generate a more realistic face image from freehand sketches. Meanwhile, this face image should respect the input sketch. So how to translate freehand sketch into a realistic face image is a very challenging problem. In recent years, conditional generative models, in particular, like the conditional generative adversarial network, have been popular for image generation conditioned on various input types. When sketches being used as conditions, they achieve quality results, only give edge maps as input. Considering the known structure of human faces, researchers have been exploring component-based methods for face image generation. However, their local embeddings learned from real images are mainly used to generate portrait images with high diversity. Conditional generative adversarial networks have also been adopted for the local editing of face images by interfaces either based on the semantic label mask or sketches. Several methods have been made to generate images from incomplete sketches, to synthesize face images from the line maps possibility with some missing face components. Due to their direct condition on edge maps, their solution has poor ability to handle hand-drawn sketches. Unlike these existing methods, which focus on the sketch-to-image translation, our works cared more about the sketching processing so that the photorealistic image could be generated even from a rough and incomplete sketch. Multiple guidance or suggestions would be very helpful for the user, like this figure. The multiple guidance or suggestive interfaces have been proposed to help users in creating drawings for better quality to provide the corrective feedback based on their input sketch. Inspired by the shadow draw, we provide a shadow-guided interface for users to input face sketches with proper structure, which would be much more easily for user to use this shadow draw guided interface. The key idea of this method is that we use the local to global approach that to reach the local detail synthesis and modeling the shape space of the face components in the image domain to build the sketch manifold. And this manifold will help to improve the robustness of the sketch to from the hand-drawn sketches. Now let us go over the details of this methodology in this research work. To train this neural network, it required a reasonable large-scale dataset of face sketch image to sketch pairs. There exist several relevant datasets like COHK face sketch database. However, the sketches in such datasets involve shading effects, while we expect a more abstract representation of faces using sparse lines. We thus contribute to a new dataset of pairs of face images and the corresponding synthesized sketches. We built this on the face image dataset of the Celeb A mask HQ. To extract sparse lines from the real images, we have tried the following edge detection methods. The head method and the traditional canny edge detection algorithm tend to produce edge maps with discontinuous lines. The AP drawing GAN is a very recent approach for generating portrait drawings from face photos. This approach leads to an artifact, leads to the although very good pleasing results. However, there are some different from the sketch with the common user. We also resorted to the photocopy filter in the Photoshop, which preserves facial details, but meanwhile brings excessive noise. By applying the sketch simplification method to the result by the photocopy filter, we could get an edge map with the noise reduced and the lines better resembling hand-drawn sketches. We thus adopt this approach to prepare the training dataset, which contains 17,000 pairs of the sketch-to-image pairs. Here is the overview of the network architecture. It consists of two subnetworks. The first subnetwork is the component embedding module. The second subnet consists of two modules, feature mapping module and the image synthesis module. Next, we will introduce each technique module in detail. Since human faces share a clear structure, we decompose a face sketch into 5 components: left eye, right eye, nose, mouth, and remainder. We define the first 4 components simply using 4 overlapping windows centered at individual face components. Here, we treat left eye and right eye separately to best explore the flexibility in the generated faces. To better control the details of individual components, for each face component, we learn a local feature embedding. We obtain the feature descriptors of individual components by using 5 autoencoder networks. Given the input sketch, we could project its individual paths to the component manifold to increase the plausibility. Since the descriptors for different components bear different semantic meanings, we designed the FM module with 5 separate decoding models, converting feature vectors to the spatial feature maps. The resulting feature maps for the left eye, right eye, the nose, the mouth are placed back to the remainder feature maps according their exact positions of the face components in the face sketch image to return the original spatial relations between the face components. Given the combined feature maps, the image synthesis module converts them to a realistic face image. We use the conditional generative adversarial network, the conditional GAN architecture for this task, which takes the feature maps as the input to generate the realistic image. Here, we adopt a 2-stage training strategy to train this neural network. In stage 1, we train only the CE module by using the component sketches to train 5 individual autoencoders for feature embedding. In stage 2, we fix the parameters of the trained component encoder and train the entire network with the unknown parameters in the FM and IS module together in an end-to-end manner. This method aimed to model the shape space of the face components in the image domain. We could use the manifold projection to refine user input sketch at the testing stage. For each component type, the point corresponding to the component sampled implicitly define a manifold. However, we do not explicitly learn the manifold, since we are more interested in knowing the closest point in such a manifold given a new sketch face component, which needs to be refined. To verify the local continuity of the underlying manifold, we first randomly select a sample and select one of its nearest neighbors in the corresponding feature space. We then perform the linear interpolation between such a pair of component sketches in the corresponding feature space and reconstruct using the corresponding learned decoder. It could be seen that as we change the interpolation weight continuously, we see that in the embedding space, the semantically similar components are close to each other. We assume that the underlying component manifold are locally linear. Given a new feature vector, to increase its plausibility as a human face, we project its these components to the manifold field. We allow the main idea of the classic locally linear embedding algorithm to project the feature vector of the sketched face component to its component manifold. The found component images are then blended at the shadow and placed at the corresponding components positioned for the sketching guidance. We compare this method with two other sketch refinement methods, by globally or by locally retrieving the most similar samples in the training dataset. For the easy compare, we overlay input sketches in light blue. The right column shows the corresponding synthesized result. It could be seen that the interpolated sketches almost perfectly fit the input sketches. To assist users, especially those with little training in drawing, we provide a shadow guided sketching interfaces. The idea is inspired from the shadow draw. When drawing, the shadow is displayed under the drawing board, and the shadow is updated instantly for each new input stroke. The synthesized image is displayed on the right. Users with good drawing skills tend to trust their own drawings more than those with little training. We thus provide a slider for each component type to control the blending weight between the sketched components and its refined value after manifold projection. We use the WB subscript C denote the blending weight for component C. The feature vector after blending could be calculated using this equation. Feeding a new feature vector to the subsequent trained modules, we get a new blend synthesized images. Now we show an example of synthesized results under different value. For the female in this training dataset, most of the subjects have long hairstyles. Always pushing the input sketch to such samples would not allow us to create short hairstyle effects. This is solved by trusting the input sketch for its remainder component by adjusting its corresponding blending weight. We can show the figures from the left to right. We must trust the weight and the hair will be much shorter. This is corresponding to the input sketches. We also do the user studies to evaluate the usefulness and the effectiveness of the system. 10 subjects were invited to participate in this study. Each of them was asked to create at least 3 faces using this system. The study ended with a question to get user feedback on 5 aspects. All of the participants felt that this system was very powerful to create realistic image using such sparse sketches. Also, we put this system into the online manner, so all the users could use this system. And at the last of this slide, we will give the link so everyone could have a try of this system. To evaluate the visual quality and the faithfulness of the synthesized results, we conducted a prospective evaluation study with the result of the globally retrieval and local retrieval. We prepared a set of input sketches containing in total 22 sketches. 60 participants in this study. Most of them had no professional training in drawing. It is obvious that our method gets better response. This video shows the synthesized faces by the participants. It could be seen that this system consistently produces realistic results given input sketches with different style and level of abstraction. We compare this method with the state-of-art method for image synthesis conditioned on sketches in terms of visual quality of generated faces. For fair comparison, we train all the network on the same training dataset, which is the same with our training set. It could be seen easily that this method produced much more realistic synthesized results. Here we show examples of the face morphing using this method. It could be seen that this method leads to smoothly transferring results in identity, expression, and even highlight effects. Traditional copy-paste method using seamless stitching method on colored images. However, there will be situations where the hue of the local area is irrelevant. To address this issue, we combine face components for generating new faces, which could maintain the consistency of the overall color and lighting. And in the DeepFaceDrawing, we could generate new faces from the sketches. And also, because the sketch is very friendly for the novice users, we could also use the sketch for the user to edit the faces. This is also the joint research work with Hongbo and Chenpeng, Yukun, Rosen, and Shuyu, Liu Fenglin. And in this research work, we aim to develop a method to edit and generate realistic images with the disentangled geometry and appearance. The disentangled geometry is the sketches. We could use the sketch to control the geometry of the faces, and also use the appearance. We could change the faces with other texture. So, real face image editing benefits various applications in our daily life. We always want to edit our portrait to make us much more beautiful or much more favorable to have a good impression on other people. However, face editing needs professional training and software. We need to be familiar with the complicated functions of the software and put a lot of time and energy into this software, such as PS. For the new users with little knowledge about the software, it is very difficult to edit the very realistic images, face images by themselves. We already know that the synthesis or generate the realistic images from the sketches have many applications. The recently proposed deep learning-based method allows to generate the hand-drawn sketches from the sketch to the images like DeepFaceDrawing. However, this method, like DeepFaceDrawing, is very difficult to infer the appearance information from the sketches, because only from sketches we could generate photorealistic images, but the texture and the appearance could not be controlled. While there for only one sketch image, there had multiple corresponding real images with different appearance. So this is the somewhat the limitation of the deep-face drawing. This method, such as from the sketch to the images, could not control the appearance of the generated images, like the skin color or the hair color. And there are some very related research work. We know that for the generative neural networks, particularly such as the conditional generative adversarial networks, has been very popular for the image generation conditioned on different input types. These conditional inputs, including the semantic mask, which generate good results, but lack of control of the detailed geometry, like Vincron. Another user-friendly interactive model of the geometry control is the sketch. We always talk about the sketch is very friendly, user-friendly. Recent methods could generate photorealistic faces from freehand sketches. However, the appearance plays a central role for the realistic image generation, which is not considered in this sketch-to-image generation method. Recent methods also propose to edit real face images with the guiding sketch, mask, and color stroke. However, these works generate high-quality edit faces with local areas. Our method further supports to edit the faces in both the local and the global manner. Also, this method treats face editing as an image completion problem with sketch guidance. They could only generate images based on the appearance of the input images, while our approach supports appearance changing from the reference images. Some other methods also propose to disentangle the attributes of real image or specific elements of images, and they do achieve attaching results. However, those attribute-based methods only support editing the specific attributes and could not achieve detailed control. Similarly, the style transfer method disentangles the style and content, but also do not support fine detailed editing. This method disentangles the geometry and the appearance of a face images and achieves the detailed control of the face generation with the sketches or appearance, or from all the detailed geometry control by the sketches, and also could we change the appearance. The appearance is from the reference images. In this method, firstly, we disentangle the geometry and the appearance of the real images. This method could edit the detailed geometry of the real image using the sketches. Meanwhile, we could change the appearance of the real images based on the reference images. Like the second row of the result, we could change the appearance by some reference images. The key idea of this paper is to design a structured disentanglement framework to support face generation and editing with disentangled control of the geometry sketch and the appearance. We also adopt a local to global approach to incorporate the face domain knowledge. Local component images are decomposed into geometry and appearance representations, which are filled consistently using a global filler module to improve the generation quality. Now, let us go over the details of this methodology, of this method. Here we need to use the paired sketches and the face images to train this neural network. To extract the sketches from the real images, we use the photocopy filter in the Photoshop, followed by a sketch simplification network. And with this paired data, we also need to train a sketch prediction network to extract sketch from wild images for convenience. Here is the overview of the network architecture. We use a local to global approach to process face components individually. This method consists of two subnetworks. The first subnetwork is the local disentanglement module. The second subnetwork is the global fusion module. Next, we will introduce each component in detail. We leverage a local to global framework to generate high-quality fit images. Specifically, we decompose a fit image into 5 components, including the left eye, right eye, nose, mouth, and background. This is the same operation in the DeepFaceDrawing, and process them using the individual network modules. Each component has a fixed resolution and is cropped from the real face image. We utilize the sketches to extract geometry information from the real face image. We first train an autoencoder to generate the intermediate features of the sketches. Both the input and output of this network are sketches. Then we train the encoder to map the corresponding image into the latent geometry space of the sketch. For the local disentanglement, both images and the sketches of local region share the space to ensure the correct disentanglement. Appearance is another important aspect of the face image. The mapping between facial geometry and the real face images is clearly one-to-many. But by specifying the appearance, such problem could be solved. Given the appearance and given the sketch, we could determine one face image corresponding to the sketch and the appearance. If we only get the sketches, there would be multiple images corresponding to different appearance. Here we employ another encoder to extract the appearance feature. The appearance encoder leverages global average pooling to eliminate the spatial information. Given independent geometry and appearance respections, an image synthesis generator takes them as input and generates reconstruction or swapping results. We adopt the adaptive instance normalization to control the appearance of generated face images. To train the local disentanglement module, we first train the geometry encoder as described before. Then we fix the weight of the geometry encoder and train the appearance encoder and the image synthesizer generator. During the second training stage, we use a swapping strategy to disentangle geometry and appearance of image. We extract the geometry feature from image 1 and the appearance feature from image 2 to generate a new image. We utilize a geometry loss to constrain it has many geometry structure at image 1. We also extract the geometry feature of image 2 and the appearance feature of generated images. Then we use a cycle loss to ensure it reconstructs image 2. This is the process of the global fusion. To translate the local image features into the complete and nature-looking fit image, we take the intermediate feature maps of the local disentanglement module instead of generated images to aggregate more information flow. These feature maps have the same resolution with the local input images. Given the feature map of the background component, we replace certain patches of it with the corresponding generated features of other components in the order of mouth, nose, left eye, right eye. Then we feed the combined feature map into the global feature module to generate a new face with desired appearance and geometry. This is the sketch-based interface for the face editing. This is the input sketch overlaid on the top of the geometry image. This is the generated face images. This is the control panel, which consists of some necessary tools such as the image opening tools and editing tools. A list of reference appearance images are placed at the bottom of the interface, and you could also load some new images by open the folder. With this user-friendly interface, users could choose some reference images to edit the appearance of the real faces. This method could also utilize sketches to control the geometry of real faces, like changing the control of the facial components and the hair structure. With the geometry of sketches, our method could generate realistic faces with different skin color, lighting, and appearance according to the diverse reference images. So the first column is the geometry. The row is the appearance. With different geometry and different appearance, we could generate this matrix images with the corresponding geometry and the corresponding appearance. We also compare this method with the state-of-the-art method for the style transfer. This method disentangle the geometry and the appearance of the image and generate new image by swiping the geometry and the appearance. We could find the result. We could look at this result and the comparison. It could be seen that the result of this method generate much images with photorealistic result and has much better result and with less artifact. We also compare this method with the state-of-the-art method for the sketch-to-image translation. Also, for fair comparison, we train all the networks on the same training dataset. It could be seen that the result of this method, the geometry and the appearance respect well, and also we generate better results in the local region. So in the global manner or in the local detail, this method generates much better results compared with other state-of-the-art methods. We also compare this method with the sketch-based fit editing method. We also use their optional editing user interface with the pretrained model for comparison. Since that this method is based on the image completion, we thus only edit partial sketches. It could be seen that our methods generate much better results, especially for the editing task. And also, the editing module in this system enables the user to join faces while coarse or fine sketches. By changing the appearance of the reference image, the realistic face images with diverse appearance could be generated. The user could control both the geometry with hand-drawn sketches or the appearance with diverse references in this system. So we could using the DeepFaceDrawing to drawing the sketches, and these sketches define the geometry, and we use the appearance from the real images, and then the real images define the appearance of the DeepFaceDrawing results. So also we could use the sketch to editing the existing images. Also we could to generate some new faces from the DeepFaceDrawing and use the appearance of other face images to change the appearance. This method learned to disentangle the latent space of the geometry and the appearance in the respective manner and enable the novel application of generating face images with the reference of given geometry and the appearance pattern. we conduct linear interpolation in the geometry and the periods latent spaces using the corresponding latent code from the given images. The results demonstrate that these interpolation phases are controllable and every interpolated phases have very high validity. Also, these two papers have been published on the StyleGAPH, and also the fast forward has been selected as the video trailer in the StyleGAPH conference. And also in the summary, the DeepFaceDrawing provides an interactive system to produce the realistic face images from the rough and incomplete freehand sketches. And also for the DeepFace editing, the DeepFace editing first disentangle the geometry and the periods from the images, and then we could edit the sketch and use to combine the edited sketch and the corresponding appearance to generate the new faces. So this is the share some similar technique, but with different motivation and different methodology. And also we open source the code, so the audience could view these pages to download the code. And also for the DeepFaceDrawing, we also put the DeepFaceDrawing online. The user could draw by themselves to generate the new faces. We also provide the services. And then firstly, thank the collaborators, thank Professor Hongbo, Shuyu, Wanchao, Rosen, Yukun, and Fenglin. And then thank you for the audience. Thanks a lot.
Okay. Yeah. Thanks, Dr. Lin Gao, for the two interesting works. And let's see. So I got one question. First question. Can we add glasses or?
We should.
Oh, okay. Can you hear me?
Sorry.
Can you hear me now?
Yeah. Okay. I can hear you. Sorry.
Okay. So the first question is, I think it's basically the same, similar to the question to Danny. Can we add glasses or hats to the sketch? Glasses or hats?
Glasses. So because in the training data set we have not faces with glasses, so it's maybe difficult to handle the glasses. But maybe this could, for the potential future work, we could using the data set, adding some glasses to train this neural network. Maybe also we decompose the face image into two layers, one layer about the realistic face image itself, and another layer about the glasses. So I think this needs some special operation.
Okay. And there's one question from a YouTube audience. It's Tong Wu. So he asked basically, how can the deep face editing handle side faces or faces with various poses?
Yeah, so this system is not limited to the strictly frontal views. We could handle offset of up to about 30 degrees. And most of the training data set consist of the frontal faces. So large head pose or for the large head pose or for the facial occlusion will affect the disentanglement effect. So we could handle some cases, but for the large scale rotation is a challenging cases because they are in the data set there are not so many side view images.
Okay, one more question is from Queen Oliver. So for deep face editing, is it easy to edit or change hairstyle?
Oh, this is a very good question. I think this should refer Professor Hongbo's newest work. So we could change much coarse style of the hair, but for the detailed hairstyle, I think Hongbo in this year StyleGraph Asia provide a much powerful work, especially for the hair. Maybe we can use that word for coarse editing, because the deep face editing could edit the face detail. It provide a tool for editing the face detail, and also to edit the hairs in the coarse level. But for the detailed hairstyle editing, I think you should refer to Hongbo's newest work.
Yeah, thanks for promoting my research. And then let me maybe ask maybe the last question. So in the both deep face drawing and deep face editing, so you adopt a local to global approach. But in Danny's like frameworks, so I think it seems like it's local to global approach is not necessary for generating realistic or ultra realistic faces. And can you comment on that? Whether it's really necessary to adopt this local to global approach?
I think this may be based on different tasks, because we want to generate the faces to corresponding to strictly corresponding to input sketches. Given the sketch, we need each part of the sketch to each line of the sketch is exactly corresponding to the generated faces. So we need the image translation neural network. We based on that, based on the image translation neural network for the local to global to divide the image into several pages is helpful, because we want to train a image to image translation, and we divide the image into several patches, we could get much better result for the translation task. And I'm not sure, but from learn Danny's work, they are doing they are not strict, need this strict exact corresponding from the line to the line of the sketches of the line of the images. So without this strict corresponding, so I think mapping or strict mapping, so we would not use the StyleGAN or some technique could directly have some good results. I think it's just for this sketching translation task, the local to global is helpful. And for generating the realistic images, it may be not necessary. It might just my understanding is maybe not correct.
Any input from Danny? Yeah.
I'm just saying that you know, many of the applications, for example, is sketches. I mean, a sketch is only a sketch, so you usually don't really want to be accurate or to be loyal to the exact lines that the user draw. So we have a lot of degrees of freedom. So we need to talk to the artist. I think maybe you work with artists. I mean, what do they want? I mean,
yeah.
I mean, to gain full control or really accurate reconstruction of the edges, my feeling is it's not that important.
Yeah, I think maybe depends on like who your target users are. Maybe for really professional artists, generally I think they would like to have more control. But for casual users, I think since the input is already not that accurate, so I think we can tolerate more errors in the sketches. But but in PSP work, the local to global approach is not adopted, but generally I think also can lead to quality results. But then the argument is how the faithfulness of the
question of how faithful you want to be. I mean,
Yeah.
What about full body? Upper body? I mean, are you thinking of extending to, I don't know, sketching full bodies?
It's a very good future work, but we are not doing that. But I think it's very useful because now only faces or head could not be put into the VR environment. If we could sketch the whole body or upper body, it could benefit much VR application. So it's very useful and future research work, and we may explore them. But we are not doing.
Yeah, I have a collaborative work with students from Swimming Pool, and also Eric is also on the paper submission. Yeah, but I think it's much more challenge than physics, right? Because of the much higher dimension of human poses.
So we're lucky. We have a lot of work to do. It's true.
Yeah, sure. Okay. I think yeah, we have make a full use of the time allocated to us, and then yeah, thanks Danny and Ling for the wonderful talks. And I think the talks will be later on. Yeah, will be kept at YouTube, I think, for the future audience. And let's wrap it up. That's the end of the second session for Age webinar. Okay, thanks again to Danny and Ling, and then also the audience. Also.
And hopefully we meet soon.
Yeah, I hope so. Okay, bye then.
Okay.